Who's doing that?
Somebody's doing what?
I think it's over here.
Wait, yeah, chill.
Okay, so that's clearly working. It's definitely happening up there. If there's anything happening. Try one last time. And if not, we'll just share the live stream. That's in there pretty good. Do you have that piece of scissors? We could just plug an HDMI right now.
I don't have an HDMI.
No, this does. This does. Just get it scissors.
Oh, first one. Wait, what are you trying to do?
This has an HDMI right here.
Oh,
Grab scissors.
Is it actually?
Yes.
Wait, can you guys just start if we just
Yeah.
Right. Yeah, so we're having a little bit of problems with the PowerPoint itself. So we do have a broadcast going on right now. So what we can do is, oh my God. Yeah. No, undo the. Okay, we hacked it.
Really get over it. Plug that into your. Nice. And then you can just move. Yeah, we'll just move the table. Sweet.
All right.
Yeah.
Even better quality than we thought. So.
1080p projected.
Oh wait. Yeah.
This is gonna be great.
Might move a little bit.
All right. Sorry about this, guys.
Yeah. So we're gonna have this as a. We're actually live broadcasting right now. So. Yeah. Let's do some little things first.
Nice. You guys see that? Okay. Good text.
Well, it'll matter in a second. But... Right.
What's that? Face that.
Yeah.
Right. What's that?
Are you serious?
Yeah, no, you do. Yeah. Okay.
Wait, let me put this. Right. Whoa. We have everything we need.
Yeah. Nice. Okay, how many of you guys came last time? Okay, that's good. You shouldn't need much stuff from last time. We're gonna kind of do a review of everything that went on last time and more, hopefully.
Definitely more.
Yeah.
Oh wait, it's what you said.
Yeah, I just have to. All right, cool.
Wait.
Good.
Try moving over here.
There's no way it's gonna do that.
Move. You have to move.
Did you get the?
All right, so I'm going to present like this. Hope you guys don't give it down. All right. That's good. Let's leave it.
Is that?
Yeah, I'm literally just going to do this.
Okay, cool.
Okay, so with any hope, let me exit out of this. Okay, so today we're going to present on the second part, which is actually full neural networks and training methods called gradient descent. And so let's see. We're first going to go over how this thing, something called a feed-forward neural network algorithm works. We're going to go over our implementation of it, and then we're going to go into the training of neural networks, and then briefly talk about deep learning. That's cool with you guys. So we'll jump right in here. So feed-forward neural networks are kind of like perceptrons, if you guys remember from last time. Actually, sorry, we'll go over perceptrons first.
Yep.
So from last time, perceptrons are weighted computational units. Basically, you have a bunch of inputs and a bunch of weights on those inputs, and you can make a decision based on that. If you remember, we had this weighted sum here. So if the inputs times their weights is more than a bias, then we're going to actually say yes to this decision, if you guys remember from last time. And basically the problem with perceptrons were they couldn't learn really complex behaviors, and they couldn't do something that is called continuous prediction, which is needed for predicting stock prices, predicting all sorts of things, anything that has a continuous output. They only output ones or zeros.
So this is where the feed-forward neural network comes in. So I guess some of the main advantages, first of all, it's a network. Like if you remember before, we talked about a perceptron network, but that isn't exactly where the perceptron started out as. So yeah, there's this feed-forward network, I guess, architecture. And so the idea behind them is that they can actually start approximating continuous functions. So they're composed of many layers, many nodes, and between each layer, they're fully connected. So as you can see here, each node in the preceding layer is connected to every single node in the following layer.
Yeah. So again, we're just going to go straight into how these things work. But the advantage of this is it's just like a bunch of stacked perceptrons. They can do extremely complex logical tasks. So to kind of explain how they work, we're going to have to get a little mathy on you guys, and I apologize, it's how it is. There'll be a lot of subscripts. So last time we talked about weights and perceptrons. So basically a weight on any given layer, so this is the 0th layer, first layer, and second layer, is denoted W subscript ij, and with L is the layer, so just for your convenience.
And this is the confusing step here. So the ith neuron is actually referring to the preceding layers connection, and or the actually following layers connection, but the jth neuron is from the preceding layers. So this weight right here, actually, let's do something more complicated.
Well, yeah, in the next, here we go.
Oh yeah, this is where we go in. So yeah, as you can see here, we have weight I2, which is this neuron right here. This is the ith neuron in this imaginary layer. Imagine there could be other stuff. We just abstracted them out. And so you see the second notations too here. I mean, that's just convenient notation because this is where most of the computation goes into it.
So yeah, so basically it functions just like a perceptron. If you think of a couple slides ago, you saw that with a perceptron, you sum a bunch of input weights and the inputs, same thing here. So for any given neuron, right, you take all of the outputs of the preceding neurons and then you sum them against these weights and have that as the input to some sort of activation function.
So yeah, you can see actually we replaced the step function that we have listed here, and we replaced it with a sigmoid here, or a sigma.
We'll explain how that works in a minute. But what's really powerful about this model is that it effectively generalizes this perceptron to many different layers and many different possible situations. So like we said last time, we used something called a step function for the perceptron model. And that was really good. You give you 0 and 1 outputs. But for neural networks, we want continuous outputs. You want to be able to predict temperatures and whatnot. So you get this continuous function right here, and it pretty much has the same behavior. Basically, you want for this thing, it's called a sigmoid activation function, have this same property as if you go towards infinity in this direction, you have output as 1, and if you go to negative infinity in this direction, you have output 0. I know this all seems a little abstract right now, but you'll see eventually why this is really powerful.
But I think the main points to take away from it is that it is compressed between these two values, similar to how the step function itself was compressed between those, the 1 and 0. So,
all right. Yeah, so yeah, the feed-forward algorithm is essentially how neural networks work. With a perceptron, if you remember, you take the inputs and you push them forward into the next layer. This thing is called feed forward because that process feeds forward throughout the network the entire way across. Essentially, you start out with an input, and you take that input, multiply it by its weights, and add it to this little net value on each of these neurons up here. When the net values here fill up, in other words, all of the previous layers nodes send inputs to them, you apply that sigmoid activation function and do the same process over and over and over. It's like a feed forward action.
If you remember from last week when we had those network diagrams, we didn't actually have this bias node here, but I just wanted to note that this bias node replaces like the notation we had before, and so the bias actually outputs like a single value, and then the weights are what define the like actual bias value that goes into each node, accumulates along each net of the neuron. Yeah. So the feed-forward algorithm in its most basic form is it goes through each layer and each neuron on the layer, then it activates. So basically applies the activation function to the accumulated net input. And then it goes through each neuron on the next layer, and it feeds that accumulated input times the weight here, and adds it to the net that is on these layers here.
Yeah. A slight note, just for you guys' understanding. There's all of this rigmarole with activation functions and weights because we're essentially trying to model what's happening in the brain. You have a bunch of neurons in your brain, and they send electric signals to anteceding neurons or like anterior neurons, and those charges build up until a threshold function or the sigmoid function gets applied, and then the next neuron fires. It's just this mathematical modeling of what's really happening in the brain here.
So yeah, now we're going to do a live demo of a live coding demo of the neural network algorithm. And so the first things we wanted to go over were like the concepts, the pieces of our network implementation. So we have a network class, a neuron class, and a connection class. The network class is composed of a list of neurons, a list of connections, and a feed-forward method and a backpropagation method. A neuron is composed of, or has connections that are to the anterior and connections from the posterior. So that basically just means, if you look back at this diagram, these connections are the anterior connections, the ones before, and then these connections are the posterior connections. And then it has an activation method, a feed method, and an error update method. So error updates for backpropagation. Activation is for applying the activation function, the sigmoid function, and then the feed method is the accumulation across the net. And then finally, we have the connection class, which has general weight information. So there's a reference to the posterior and anterior nodes. So go back again to this diagram. Basically references to the posterior, the one that comes before, and then the anterior node, if we were talking about this weight specifically. And then it also has a weight value itself and a feed forward method. So yeah.
Yeah. So basically, we want to start with this neuron class, right? How do these things actually translate into code? We've basically broken everything up into separate classes.
If you guys want to follow along, actually, why don't we run through that too?
Yeah. Do you guys have any of you guys downloaded any of this? No. If you want to follow along, at the end, we're actually going to let you guys play around with training your own neural networks to do whatever.
So yeah, you can.
If you go to GitHub.com, I think the link will be in Facebook.
Yeah, actually, why don't we post it real quick?
It's already posted.
It's already posted?
Yeah.
So it's philcuz, github.com/philcuz/NN workshop. So if you do have Git, all you have to do is copy Git, clone the link here. Or alternatively, you can just download zip. So actually, why don't we do that real quick? It's like sizable, so it'll fit. I mean, you can download it right now. So open it up in your text editor. Oh no. All right.
No.
Okay. That usually crashes. Adam.
Okay.
All right. Yeah. And yeah, here we go. So we can start coding.
Yeah. We've provided a bunch of. Oh yeah. What's up?
I had a quick question about this second to last slide.
Yeah. Sure. Yeah. Feel free to ask questions, by the way, guys. We're like moving pretty fast. All right. Yeah. What's up?
So,
This one?
yeah. Is that diagram just like the perceptron, except with a different activation function?
So, yeah, pretty much. I mean, we're thinking of so the perceptron has this diagram, right? You have a bunch of inputs and you sum along them and apply the step function. And the same thing with a normal neural network, you do the same thing. But the way we're gonna implement it is actually that you have a neuron, right? And it has a bunch of input already. You activate the neuron, so you apply the sigmoid, and then you just send the output of the neuron to the next layer. It's kind of like a recursive thing. So you start from the inputs and do this. We won't implement it recursively, but that's essentially the process that's going on here.
So it's like weight, then sigmoid, then weight, then sigmoid, and so on.
Absolutely.
Basically, yeah.
But if sigmoid is always like between -1 and 1, won't the sigmoid like decay?
So what happens actually in training is that what you're talking about, something is called regularization. But in general, when you're training, you're building your network towards that data set. And so these weights can be very large, right? So let's say you have sigmoid weight in this thing, right? This weight could be, 200, right? 200 times 0.01 will bring this back up to kind of a normal value, which will fall in this range right here. So if you're looking, in our demo, we're using the tanh function for our sigmoid, so it'll fall somewhere right in here or wherever. But the network, as you train it, and you're going to see this, will actually account for all that. And ends up working pretty nicely, if that makes sense. Does anyone else have any questions on the math? No, that's a weird way to start, but we're gonna jump right into coding it now. So we provided a bunch of classes in here already, so we can just focus on the main parts of the feed-forward algorithm.
So yeah, if you're following along, open up neuron.py.
Yeah.
And we're gonna start with the feed-forward function. So the first thing we want to do is code the actual accumulation of the input across the net. And basically that's just done with self.net and plus equals input partial.
So again, this is just in the slides right here. You're feeding basically a weight times the output of a previous neuron in here. That's what input partial is. So yeah, all right. And then now we're gonna, so that's pretty much all that does.
Yeah, and then the next thing we want to do is add the activation function and actually call it. So the first thing we need is the application of this activation function on the net that we've accumulated. So basically we just do self.gradient.output is equal to self.sigmoid.map self.net.
Yeah, so we just provided this little sigmoid class, which contains it's pretty much wrapping a function.
So the map part of it is the actual function itself, and then there's another part which you see on the screen already, which is just derivative.
Yeah.
So which becomes important later in the back propagation. So after we've applied the activation function to this neuron, then now we want to go through each connection in the posterior. So basically all the outgoing connections and feed forward. So call our feed forward method that we're about to define in the connection class. So all this simply does is takes in the output and then multiplies it by the weight and passes it along.
Yeah. Right. So then we do feed forward. All right. Cool.
And after we do all of this, we want to reset the net. So for future feed forwards and all right.
Cool.
Any questions?
Anyone know what's going on right now? Okay.
Yeah, we'll come back to it if you're not sure. But yeah, feel free to stop us at any point too.
Also, we provided the solutions for what is actually what the algorithm is in the folder. So at the very end, when we get to the demo, if you haven't followed along or you have no idea what's going on, you can play with it that way. But yeah, so that's just essentially the algorithm. Just to recap, right? You have a given neuron. We're just going to call this AJ. You activate it, and that basically means send apply the sigmoid activation function and then feed all of these things into the next layer. That's exactly what we just coded. And we've wrapped it all up in these pretty methods and have a general purpose thing in the network class that will handle all of this. But that's basically what's happening here.
All right. So now we want to move on to the connection class. So open up connection.py. And the first thing we want to define is the actual feed-forward method. Actually, it's the only thing we need to define, and that one's pretty simple. We just go to our posterior neuron, feed it the weighted input from the previous neuron. So it's just self.posterior.feed, self.weight times self.anterior output.
Just all from the slides that were happening. Yeah, that should be that. Now we want to go to the network class and actually fill in this feed-forward algorithm. So at first, basically we've constructed all of these neurons. We provided all that code. It happens here in the initialization function. And we're going to provide a training function later on. But we also provide a feed-forward function, which is you take input, array, and it'll actually push it through using this algorithm and then output finally.
So yeah, the first thing in our feed-forward algorithm, the first thing we want to do with our feed-forward algorithm is actually apply the inputs that we pass into the method into the first layer of neurons. So we're able to do all the feed-forward operations. So we want to make a for loop that goes through all of the pulling of the inputs. So for I in range len of inputs. Yeah. And then we want to do self.neurons, the first layer, so 0, and then each index of that. So I and feed inputs into there. Oh, inputs on. Yeah.
Can you move that up? Okay, sorry. Move it up here.
Yeah. So yeah, now what we want to do is actually pass all these values through. So the first thing we do is activate the bias, and that basically just passes the bias into every single element, every node in the graph. Self.bias.
Yeah, self-bias.
Yeah. So since it is a object that you've got to self-reference it. And then what we want to do after we activate this is activate all of the neurons successively. So for each layer in the neurons, and then for each neuron in the layer, we want to activate.
So yeah, this is essentially what's happening with the feed-forward algorithm. You're just going through all of the neurons in every layer successively and activating them, pushing everything through the network.
And then after that, we want to grab the output from each of the last neurons. We've already written this, so that's what the last line does there.
So hopefully if we've coded everything correctly, which I have no idea if we have, we're gonna actually be able to run this algorithm. So basically what we've done is this network class will construct any network you define with a bunch of random weights and any given structure you want. So we've created something in the demo directory, if you're following along, and it is also in the solutions directory, which handles all of our imports. So you can run Python on it as an import. I use.py. So basically we've created a nice little syntax for you to actually make a network. So if we want to make a network that's, let's say, has two inputs, 3 nodes on the hidden layer, and 1 on the output, you can do something like this. And then we can hopefully feed forward, hopefully, let's see, yeah.
Just do one.
Yeah, 1. And it's, again, it's either a tuple or a list. Oh, whoops. Sorry about this, we're in the wrong directory. Right. I don't think you pulled, Phil. Yeah, go for it. What's on there? See the demo. All right,
now we can work.
Now let's hope. All right, wrong directory. Good. Oh, great. So we have some indentation errors. This is great. Right, self.net, and then neuron connection. Yeah.
Try running it again.
Yeah. So this would be,
Yeah, just open up the solution. So because we had an error with our thing,
we're just
gonna
gonna
open up the
solution.
Just to demonstrate it, but
all right. So we'll just do this network thing again, make a network, and then feed something through it. Right now it has a random output. So
if we regenerated it, you can see actually a different output
Yeah.
as well. The whole goal of actually running the backpropagation will be to like avoid this randomization and actually get meaningful output.
So yeah, basically we have like this network class, and we want to figure out a way of training all of the weights in the network. Because if we can train the weights in the right way, if we set these guys up in the exact way we need to, we can model pretty much anything. And that's what's so powerful about neural networks.
So for all of you who were here last time, if you remember, we mentioned that the whole goal of machine learning is to adjust learning based on like adjusting these network parameters. So in the case of neural networks, these network parameters are the weight values and the bias values that are across the network. And so what we do is try to minimize the loss function, which is basically just an error function from the desired output, which is provided in the data set, or which is a data point in the data set, and the expected value, the actually output of the neural network itself.
Yeah, so if you remember from the notation way earlier, yi is the output of the network, and delta I is going to be a desired data point. So in the case of the XOR data set, this isn't even a full sum. It's basically the desired, which might be 1, minus the actual output, which might be like in what we just saw was like 0.99876, some number that starts out completely randomly from the neural network.
So a big problem with this function itself is that the problem kind of construes this has this non-convexity to it, which basically means that the solution is not very calculable through mathematics itself. So we have to do some kind of sneaky ways. We have to develop some sneaky ways to actually go through and solve the problem itself.
and which are called heuristics.
So in particular, neural network practitioners, for the most part, actually use something called gradient descent and error back propagation.
Which is just an implementation of gradient descent.
Yeah, so basically what happens in gradient descent is you build an error function for the neural network, right? How bad is it doing based on what we want it to do? And you say this error function can be written in terms of all of the weights, because we're trying to pretty much optimize the weights, right? That's how we define our error. My weights are really good, the error should be really low. So basically you define this function, and for example, this one I've only provided a visualization of it when you have 2 weights in your network, which is a pretty small network anyway.
But in a realistic network, we could expect like dimensions of like
Millions.
26.
Yeah, you could have a million-dimensional problem, but essentially you build this weight surface, and you start at a random point. That's basically initializing your network. You have a bunch of random weights, and you might start somewhere here on the axis, just on the plane below, and then that gives you a certain error. And the goal is, how can we get to the bottom? How can we get to the lowest error point? And in calculus, there's something really convenient about something called the gradient, which is just the slope at a point. In multi-dimensional calculus, what you can do with a gradient is there's a notion that the gradient points in the direction of greatest ascent. So if I'm standing on some hill and I take the gradient of my position on this hill, that it'll be basically an arrow pointing in the direction of the highest point on this hill. And that's really useful. So what we can do is, starting at some point on this really crazy high dimensional weight surface, take the gradient and say, all right, go in the opposite direction of this gradient. And that'll be pointing in the direction of greatest descent. And that's why you call it gradient descent. And what this translates to is something called error back propagation. We're not going to get into it because it's really mathy and kind of convoluted to understand in one little lecture, but we'll explain how the weights are updated.
And if you are interested in looking into that, come talk to us after class. We can give you some good references.
Do you mind if I do this?
Yeah, good.
All right, so again, the gradient is basically a vector of partial derivatives. This is really calculus heavy, so you can start sleeping if you don't know a lot of calculus. But essentially, you get this gradient somehow through error back propagation. And using this gradient, we can think of all of the weights in the neural network being this gigantic vector with a lot of components, maybe 1 million components. That's how many dimensions or weights we actually have. And then basically, you just want to change the weight at a given time step by taking the negative of the gradient, so moving in the opposite direction, and multiplying it by something called a learning rate. And you'll actually, when we're coding up, when you're actually playing around with the training demo, you'll be able to change the learning rate and see how it affects learning. But the really cool thing about this is, in a lot of problems, gradient descent works excellently. It really takes all of the weights in this random network and descends to really low error. And you'll see that with XOR and a bunch of other data sets we've implemented. That's fine. All right. Okay, so basically, at this point, we're gonna let you guys play with the actual full solution. And just on a basic, very Python level, you're going to be able to create networks with the syntax. So you'll have like
Yeah, just a quick explanation. We, as you saw before, we had the network creation with the n equals network, or some whatever variable equals network, with the list of the layer sizes. Then there's a trainer class that we provided, which basically takes in the network itself and then starts running over it with the data set that you load in. As you see here, we call it t equals trainer n, which is just the network object. And then we load the data from a separate file itself, which we've provided, I think, three that definitely, or yeah, three that work.
Sets, yeah.
And there's one that doesn't work. And then there's an interactive step here. So where you provide the learning rate, which is basically the amount that you actually descend in gradient descent, and a optional flag that actually shows you the changes that you make across each weight itself.
Yeah. So we're actually going to get into like, let's try something last time. Last time you guys struggled making XOR. Like it's kind of a pain to manually do that. So what we can actually do is, if we look in this directory, if we look in the dataset directory, so it'll be here, datasets. We've actually just made a nice little dataset, and I'll show you the format for that. Let's see, where is it? Zoom in a little bit. Okay, how do you do that? Yeah. Okay, so basically, this is how we format the data sets. You have two inputs for the neural network. 1 and 0 goes to 1, right? 0 and 1 goes to 1. 0 and 0 goes to 0, and 1, 1 goes to 0. Just the normal XOR function from last time.
So as you'll see, we can actually input these into the network trainer itself. and be able to do those complex operations with it.
Yeah.
And basically, instead of actually coding for it, which I mean, although in this case it seems kind of like trivial, why would you not just code for it? But but in this particular, this kind of shows the power of neural networks to learn at least this function, and we hope that it kind of the idea translates to other ideas too,
So
to other functions that we may want.
let's make a network, right? So we'll have 2 inputs, maybe 4 on the first layer, and well, let's make it 5. Who cares? And then 1 output, right? So it takes 2 inputs, 1 output. Then you make a trainer, so T equals trainer on this network. We load the data set. You guys can feel free, if you go into the solutions directory, like actually start messing around. Yeah, data sets / export data. Right, and then we can actually do this interactive step function, which is just something we made nicely to train. So I mentioned that there's something called a learning rate parameter. Basically, this is kind of the bane of neural network practitioners. You actually have to kind of choose at random what learning rate you're doing. And there's definitely certain intuitions you'll get for how it works later on, but it's just kind of choose the parameter and see how well it trains. So this is, you can see actually after 1 epoch, or let me do this verbosely for you guys. Okay, so basically the trainer, you hit a key and it does 1 epoch of training. And what that means, it goes through the data set, and for every point, it'll actually train the neural network on that point. So in this example, we have a data set, right? Again, 1, 0, 0, 1, 0, 0, and 1, 1. And you can see the neural network takes this in, and we desire this 1 over here, but the output was 0.6. So the error right there is pretty bad. Again, same thing happens here, 0, 1. This is just, you can see the error is pretty horrible on all of these, right? Error is very high. We want to get the error to something below like 0.001, right?
So this training error is basically just the sum of all of these previous errors throughout the network itself. So yeah, we can just keep going on. We see like small improvements, but it'll gradually get more improved until it's like extremely low. And at this point, it's almost trained to the maximum that it can be trained.
So once you're done training with this little tool, you can hit Q and actually try feeding forward stuff. So if we go like take the network and we feed forward, let's try XOR, right? We'll try 0, 1. So it's getting really close to 1, whereas before it was like -0.9, and you can do the same thing for other inputs. Oh, my bad. So yeah. 0.85. This is the probability basically that the network thinks it's 1. And then you can try it with 0, 0, right? Very far less than 1, and then 1, 1. Again, very far less than 1.
So yeah, of course, this network still needs a little bit more training. So we definitely run it through. We definitely need to run it through a few more epochs, basically. But the main point is that only after a few that we're actually getting close to this these values that we actually expect.
Yeah. So like we're gonna like let you guys now play around with this if you guys actually have Python.
So yeah, the first thing you want to do is actually try out this XOR site. But then once you're done with that, and if you're having some troubles figuring it out, we can help you set up the other data set that we were playing around with before, the tic-tac-toe data set. So basically, the whole point of the idea behind the tic-tac-toe data set is that we can it has all of the tic-tac-toe possibilities. All of the game possibilities, and it will give you a result of whether like one player wins.
Yeah. So basically, it takes in the inputs for tic-tac-toe, right? So you play a game of tic-tac-toe with your friend sitting next to you, and then you want a neural network who will actually have learned what the rules of tic-tac-toe are, so that it knows who won the game. And what this thing does is that it has 2 outputs that effectively says, okay, O1 and X1, and basically you can actually kind of train a neural network on this. It does work. Really? Yeah, there's no data in.
We have to find the data real quick.
All right, but I'm just gonna turn it over to you guys, and if you don't have Python set on your computer, like you can come up here and we'll just play around with it if you guys want. So yeah, go ahead and train neural networks. You have any questions? You have no idea what the hell's going on, so like come up here.
Yeah.
Yeah.
What's up?
Some missing modules in solution.
It's the worst thing you can do.
Wait, so C good. Well, I mean, did we push?
Yeah, maybe we just gotta push again. Alright. We not. No. Okay. So I mean, try it for now. I think everything should work. But yeah, are you guys also having trouble too? Or
Yeah.
just you guys?
Okay, we pushed. Yeah, I can actually explain it to you.
Yeah, I mean,
But-
anybody
but
else
like
with,
you-
like,
yeah.
yeah, I can handle problems.
I'm
Okay,
just,
so.
You're just here.
I'm just here.
Yeah, definitely listen to him. He's gonna go over some.
Well, so
some stuff,
do you
yeah.
want to know how training works? I guess like, specifically. All right, cool.
So for anybody having import errors, you may have to clone again. I mean, not clone again, pull again.
Okay.
So we forgot to push a change, or alternatively, you can copy all the files in your solutions directory into the main directory, and it should work properly after that.
So
So it basically the solutions directory into the parent
you
directory.
can break this data set, or you can fix the whole problem basically into like inputs. So input vector x, which is just in 2 dimensions, right? So this is x and r2.
Again, I'm not sure if it works in Python 2, but Python this was written in Python 3.
Same way, right?
So-
You have some input vector c and some output vector delta. And what you want to do is you want to take this model and move it so that these weights. So when you input c, you get delta out, right? So basically, what you want to do is
Oh, what's
find
up?
this error function, and there's like a whole way.
What's going on here?
Tiny error function.
Sure thing.
So
Training
you basically
the
say the
251
error is
network
the
for XOR
Euclidean
data.
distance.
And so I get
Between
0.0, and then if I
output
do it again, I get like
Tell me
0.3,
if
so
I
it goes up.
Yeah, so at some point the network is gonna overshoot the value, so that usually means that the interactive step that you're using is a little bit high. And so actually, if you just press Q for now, you can always resume training. And then let's just see what you did. 0.5. So I guess in our case, 0.5 maybe was too high. So if you try something like 0.1,
you start up here.
and then yeah, just try that out. I think it may be less volatile. Yeah, see, it's like a little bit better. It's like more directed.
Oh, wow.
Yeah, so that's kind of a weird heuristic that goes on with that propagation itself. So if you remember the ball,
Did you get the gradient descent thing?
the gradient descent kind of example that we had before,
So you want
The-
to like get this gradient for
Is
the
that
weight vector. So
the,
you want to get
um,
delta E or lambda.
how it trains is it tries to find
Right.
minima. So if we
So how you do
simplify
that
it
is you
to
literally
basically,
go to this error function and you take partial derivative. So doing that, so we say
or I'll pull up that
What is
diagram
del
that we had
E?
before.
del W.
We
just the goal is to calculate these partial derivatives. And to do that, you have to go and look at this error
Oh yeah,
function
okay.
and say,
You're right. So
this-
what can
this
happen
y
is, let's say
is
we're
the
here
output
and we're
of
just
the
traveling down.
y1 and this
What
is-
will happen is it overshoots and actually ends up somewhere over here instead of actually ending up somewhere
You have
more
markers?
closer to here.
Okay.
So that's why we want to sometimes play around with this interactive
I
step
did a lot of stuff in high
that we
school.
choose, and
I-
I mean not interactive
Yeah,
step, but this
studying.
learning rate that we choose because it basically
There's
just
some
determines
actually
how
really
far
great
it goes
stuff
along this
on-
gradient.
So many great resources. That's like
It's kind of like a ball.
Really useful.
Exactly. Actually,
Because, like,
there's a
like I'm shoving all in one.
actually it used to be there, but there's this diagram that just pretty much shows the exact same thing. The whole idea is that you try to roll this ball and try to minimize it into there. So, of course, sometimes if it's going fast enough with, say, a high learning rate, it will overshoot the actual minimum. Just keep going.
So and it's composed of these waves.
But that's also why you see it kind of like bounce around too.
Yeah.
Same idea.
So you take partial derivative here, so it's like the sum of.
Anybody having
So
any problems?
actually, in particular, right? Let's actually do a specific one, weight 1, 1, right? So this sum right here, basically the only variable which depends on this weight
Yeah, sure thing.
is y1.
Oh, let me.
Not y2, not y2.
It's actually like how to
y1 is
run this.
connected.
So
So
when I'm like
basically, we can eliminate. We'll
opening up the file location,
delta 1,
the XOR file is
one squared.
Is this part of?
Let's see.
plus
So I think
Delta
there
2
could be a
minus
problem with
y2.
the // unfortunately because
This
you're
y2
limited,
doesn't
right?
depend on it, so
Um,
get rid of it.
Yeah.
And the partial derivative with respect to this guy
Maybe it's dot.
is just you take the square away, and then you take the partial derivative of the inside.
Ooh, that's a good question.
So
Hold on.
del
Um,
1, y1.
Python.
So what is y1? You remember the equation except y1 is a little bit the sum of.
I would.
So
I mean, I don't know. How
this
much coding experience do you have personally?
Yeah. pretty much. So let me just expand this, right? So you,
What?
Well, I'm gonna write right here.
You're a freshman? Okay, yeah. Are you what major are you?
So what happens now is right.
Okay, yeah. So I would recommend just like checking out Linux as well. Because Linux is just nice. Has you don't have to do some weird hacky stuff to get like all the same functionality and stuff. It is very similar to Mac because they're both like Unix.
Linux operating system? Or like,
Yeah. So there's
right?
the operating system itself. Of course it's a commitment, but like do a little bit of research. I recommend Ubuntu. He actually is running Ubuntu on his Windows.
The derivative of spectrum.
And so it's just nice because you get a lot of like extra commands.
And what's the derivative?
Let's see.
It's just going to be times a1, right? So
I don't even know.
times. So this is just a1.
Is it just like C?
Right? That's like
Is that not it?
a very simple way of calculating this partial derivative. And you can do this for all sorts of things. You can also do this for the beta.
Wait, what's
right?
it?
So yeah, we're trying to do basically the same thing as .. / in Windows.
It's
Yeah.
dot dot.
Oh,
backslash.
hold on.
It's dot dot backslash.
Oh,
Wait, did you caught?
It's dot dot. It's dot dot backslash.
No. I think there's another problem.
Okay, so
So
this is. You could do this over and over again.
what
right? But
directory are you in?
there's-
Did
there's
you
a
move all
problem
your
with it. If I were
solutions
to
into your?
have a
Oh,
network
you know what? That's a
of
different
ways, it would
So
really
it turns
cost
out that we're
every
in the
time
right
to
directory,
compute
so
this,
we have to do
like,
/ Okay,
symbolically
yeah.
compute this derivative.
okay.
So we can do is
Um,
actually kind of generalize.
So
these
let's go
features
back to that
of what
reference. I think now you just have to do t.interactive step.
application
So yeah, try that out.
And like, there's a really cool intuition.
T.interactive
So
step,
let's
and then
say
you want to
it's
set a
huge.
learning rate. You said this is XOR, right?
Yeah.
What network? You did 251, right?
And this will make it simple because the error function is
Your
not
network
a sum
structure?
anymore.
Yeah, I think you
Yeah.
did 251. So do 0.1.
I'm not gonna draw these out. Anyway,
T.interactive
so the error function
underscore
in this
step.
case is just equal
underscore
to
step.
delta I.
And then do 0.1. And I would do true as well, just to see.
Right.
Sorry, true.
So if
Yeah.
you wanted
Oh.
to calculate the
Yeah,
derivative
yeah.
here, the procedure for error propagation is
Right, and there's just press any
as
key except for
follows.
Q.
So for every node in the network, right? So
Sweet.
starting from the
Wait,
output,
wait,
node,
wait.
right? So for this node,
What is happening?
assign it
That's a
something
massive
called an error
transition.
collection.
Okay, there we go.
It's getting better.
All right, we were just
So-
doing some weird stuff.
This
Why did it
guy's
start
E,
that high?
right? So for
I mean, it's the randomness of it. So I assume that you just so happen to choose like the most
delta I
random
minus
set
yi.
of possibilities there.
So like the worst set.
Like pretty close to the worst set. Yeah.
Basically,
Yeah, okay.
So let me preface this with something.
I mean that's good. I was a little bit wrong.
What were the
Think-
inputs?
Before when you
0.1
saw how
true.
partial derivatives expanded, like,
So this
You
is
got
the
a bunch of
XOR algorithm
chain
itself.
rules, right? A bunch of terms you could break up.
Or
and
not
multiply.
algorithm. It's like a logic gate.
Yeah.
And are you familiar? You're
Well,
familiar.
the thing
with
is,
XOR?
if we kind of
So the
memorize how
XOR
this
is
is
kinda-
happening, right? So
it's
store
just like
the first part of the
manipulation
multiplication
of those two.
in this node,
So
and then multiply
that
it by whatever is
operates
multiplied here, and then
like
do that
so,
over and
yeah,
over
you
again.
can write it true.
We've effectively prevented ourselves from doing this over and over again, right? Because this is stored
It's just like
in the
Yeah,
X.
yeah.
But anyway,
So
this is the
it's
procedure.
XOR.
Take
It's
it-
exclusive.
Take a node, set its error
So
code.
basically what it
coefficient. For
is,
the output layer, we just do this. E
when it's an
is
and,
equal to delta
then,
I minus yi
like,
times
if an
T
and
prime
statement, we're
of
trying to
the
show
net
you.
input. And if you remember,
But
from
that's
the
like the
exact
one.
same
That's what's
thing
different
as
one
the first part of the multiplication.
Yeah, so that's
And
why.
then
Oh, completely incorrect. My
Okay,
bad. Yeah. The zero. So the 0.1.
So just
it's called
whatever
the
net part is. So now if you
the
take a node
learning rate,
anything but the output,
and,
what you do is you say right here. So E
Yeah, let me just
is equal
actually
to
scroll up real quick.
this weight.
So if you notice that we had this graph before, right?
Weights
And so the whole point of the
So
learning
weight
rate is that it dictates
Ij
how far along this gradient you
times
make.
the
So if you're kind of
Almost
familiar with the
six
gradient,
I
it's basically like a
Ei.
slope along
so
graph,
weight
right?
ij
And
times
a slope
the error
here is going to be
coefficient
like
of
pointing down to this direction
the
here. And so
next
the
layer,
idea is that you want to travel along it. in a
so
certain
that's
rate.
just we'll just say that's
when
I.
you travel along
And then we
it,
multiply this
like,
again by
you need to determine how much you
G
actually travel along. That's what the learning step does.
So G
But what can
prime
happen is like, let's say
into this.
if you don't mind me doing this,
So I know this seems a little bit arbitrary, but this is basically
Um,
what happens. The intuition is that
whatever. I'll show you on mine.
change weight
it's not
based on
stopping.
how much
Let's do this.
right like that. And so
So let's do a network.
this G
2,
prime
5,
kind of
1.
ancillary, and you can actually kind of remove it.
T equals
anyway. But in terms, it's just the error contribution.
Yeah,
like
sorry, I'm
out the
not
node is
really
just
speaking
this,
it, but
right? Then you
just
multiply
get it
by
done.
all of the weights.
Data
that
sets
lead to
XOR.data
This is the way we want to change. I take
T
and
dot
then
interactive
suppose
step.
that this
Okay, and so
it's just E times-
let's just do
so-
let's just do a
so E is equal
0.5 run.
or sorry,
So this is much higher than the one that we chose. And what can happen is that
essentially equal to.
so we're getting close to the minimum, right? And you'll start noticing that now that we're really close, we're like at a point where the actually interactive step is going to start messing up with stuff. Did you notice that big jump right there?
Yeah.
There was like we're at 0.5 here, and we're at 0.7 now. I mean 0.27 now, but I guess it's going to jump again. And so the idea behind like choosing the right interactive step is that you don't want to overshoot.
Oh, okay. So yes, exactly.
That can happen.
Make it smaller, it just takes more
You
steps.
calculate. but it's more
Yeah.
accurate.
So
Error
it's trying to figure out this like medium between like computational, like complex or computational
calculate
needs, I guess, and you know, actually approximating it pretty well, rather than like the overshooting.
So you do, and
So in like a bigger network, you're gonna start running into problems with like actually calculating.
let's say we're
So I mean, let's say for some reason we wanted to make this like really convoluted
right? So this
network where it's like n
n
equals
of these weights
2,
times the error coefficient on the next layer.
400,
It's actually kind of like
300,
So
20,
we just say the error coefficient 1 here.
and 1. Yeah,
So
that
this
should
guy's
be
error
excellent.
coefficient is equal to
And now we put that into the network of the
sum.
network. Okay, and we do the interactive step. You'll notice that it takes.
1 I times
It's like
the
that
error
broke
coefficient
something.
there.
But
So it's actually kind of the reverse of
what
before,
just
right?
happened?
You're taking the sum of all the
Oh,
powers, and this is just like
okay.
because of change.
Yeah, I know why. Didn't actually make this a network.
So it's the sum of all the contributions of error from a given point, if that makes sense, at like a very high level. And then that's how you change it. You multiply it by
Wait, I didn't
the
actually
parameter.
send it.
But this kind of memoizes it. So you're really back propagating this first initial error, right? Just by,
Yeah. Right.
That's a,
Well, almost got it.
it's not the most intuitive way to get at it.
Once you have this, these error coefficients, where you know what to do with that.
Okay, so let's say you have your error coefficient.
Okay. So yeah, when we run it, it takes so long to go
In
through.
particular, the
Like,
error coefficient.
And you just saw how much that
Training
increased. Instead of instantaneous,
Let's say we're
then
changing
now it's like crazy.
this way,
The training. So if we were trying to run it a bunch,
right? And you have an error coefficient right here.
hopefully this will just like let it run a bunch. Just kidding, it
Right?
doesn't.
So you're changing this way, and we've calculated all the error coefficients and
So-
weights. Suppose we've done that for every other thing.
I don't know how well this will
But
train because
change
this is
in
a
this way.
ridiculously sized network, but I mean, it
It's
still
still-
approaches. It still works. Like, but it's of course it's like
Is equal
there's
to-
still like the error, the
Alright.
problem where it's like
error.
So it's just running that
contribution
same,
here, right?
it's
So
running the
this
same
means
training through like just more neurons.
times-
you know what's kind of interesting though is that the error that
So,
we're
in other words,
outputting
like,
right now
it's equal
is
to
probably like
how
a
much
lot
this weight
smaller
has
in
affected
comparison to the
everyone
other error before.
times the
So
last.
because this is actually the sum
And,
of
like, it happens
But
though.
am I
I'm not
completely
going
wrong?
through full derivation of it.
yeah, this is the sum across every single weight.
It would
So
be redundant.
So-
This is
e to the
essentially
negative
what's happening, right? So I'm taking this error
yeah,
coefficient
it's kind of ridiculous, right?
Yeah.
That's the exponential
Um,
weights. Right, so then you store this del E.
Let me see.
And then
Let's see if we can
after
do
you
something with
air
this.
back
So
off the
n
errors,
dot
you calculate all the gradients, you then update.
feed
So
forward.
a bigger network is always going to be more
Whether
accurate.
you-
Exactly.
is equal
Well,
to negative
yeah,
alpha.
but of course there's a trade-off, like computational power.
and then you W.
So actually, this is really good. Like, all right, wait. Just kidding. It's not. But
I can explain
don't worry
it.
about it. Yeah. So I guess so. This is still not properly trained. So we're still getting some errors here. But yeah. So I guess the error here is actually a lot higher. Never mind. Scratch that.
Yeah.
15 trials.
Yeah. That is also the
15
case.
trials to go through.
So it's not exactly.
So of course, it's like trying to figure out the correct interactive step.
You're composing it, but yeah.
I mean, we're good.
You have a question?
Exact question.
Wait, you have a question? Yeah.
I was explaining about how things in what format is the low data method take the arguments in? Like you have to do the full value.
No, you have to do a relative.
Yeah,
path,
pretty
which
much.
is your
So
relative
like-
path, correct.
And so,
So
is that
what
why
directory
you,
are
like
you
you have to initialize solutions with
Solution. So it should be dot
random values
Well,
and have them be like high.
Oh, yeah, make sure you have the string
So-
there.
the way you initialize weights is you take like a Gaussian distribution around 0. And that's just because empirically, apparently, neural networks do better that way. But
Oh,
it
there
doesn't
may be a
matter where
problem
you
with
start. You can
tic-tac-toe,
start out
actually.
with weights
Oh,
being 1, 1,
So,
0.
Which one?
yeah, let me
me
link you to
if
the
the
better
weight was
file.
0 or really close
Or
to
let me
0.
like update the file.
I mean, it doesn't matter. I can create another.
Yeah,
I just want to see.
No, tic-tac-toe is probably the best one. Let me just roll back.
Right.
Whatever.
How will it change?
Yeah. So what happened? We like accidentally deleted it in.
So if the weight is 0, right? The partial derivative actually never depends on the weight, right? At the end, right, it's the error coefficient of the next node times the output of the previous. Right. So even if it's 0, it's not depending on that, right? It depends on how big the output here was here and how much having this node be 0 or this weight be 0 actually affected the error.
So what's the
Maybe I'm not understanding
learning
this
rate?
Say you go through it one time.
I'd pass it for which one?
You do the error rate times
For
the
tic-tac-toe would be a good
So
one.
you
It would
do that.
be,
Oh, so it,
I think maybe
up here,
0.5.
right? If this
Try
time
that
is
out.
0,
If it doesn't work
right?
out that well,
And
then
you were
try
truncating
something a little
backwards,
lower.
right? So yeah, at this point, right, this error coefficient would be like.
You may want to check the
it's all
file
happening
because I
0,
think what
right?
happened is that we deleted it by accident.
These
So-
weights have to be 0, right?
Check
This
the
error
inside of it. Is it
coefficient
just
now
empty?
0. It's useless.
Actually, yeah, it is
And
0
then-
bytes. So
this is 0.
Yeah, I think it's
All
empty.
these
It should be
0
like
out.
a lot bigger than that.
That means this weight is not. It means these weights will be, right? Because the output, right? The bias. It's really important that you start out with a non-zero bias. That's the only thing that matters. Because to change this weight, right? So on the first round of error back propagation, the partial derivative of this guy will be 0, and we don't even know how to change it. But here it's going to be equal to this guy, A1, so times the error coefficient here, which is just the difference. Right, so it's going to be A1 times, on the output layer, the delta I minus Y. Right? So A1, there you go. That's essentially what's happening, right? It's just going to be, the partial derivative here will be positive, it's guaranteed, or negative, depends on how it changes, but it's not going to be 0.
Man.
So this weight will change, and then on the next iteration, we'll have like 1.7. On the next iteration, this weight is still 0, but again, the partial derivative is now going to be non-zero because this thing is non-zero. It's going to be like 10 or some whatever number. This is like 7. That makes sense.
Yeah, kind of.
And it's a really hard algorithm to like.
Again, that step where we have 0 to then we have positive.
Okay, yeah. So like, say 0. And you take the partial derivative perspective.
Yeah, sure.
You guys are the robotics
That
club,
is
right?
going to be.
Yeah, we're associated. The coach is more part of
difference
robotics.
over here.
Oh.
So if you want to talk about
YI
robotics
minus
at Berkeley, talk to him.
what
Yeah.
is the output.
Yeah.
That you want minus the output. So it's going to be 1 times the gradient.
Okay, yeah, I'm gonna send out an email.
About 1 times
Have you signed up
the output of the last workshop.
Yeah.
Okay, great. So
Okay, yeah.
it's 1 times
I'll
output A, and output A is non-zero.
Yeah,
So that's going to be.
Okay, there we go.
That's going to be a real number, right? That's going to be a positive number. 1 times a positive number. So then we have the gradient is a positive number. And the gradient is then in turn a part of delta W. So delta W is positive, and then we just add delta W to the weight, which happens to be 0, and that will change the weight value. So then this will be like 1.7 the next step. Okay.
that counted on the output of A.
And it's really simple, right? The output of A is what? A11 is equal to G of the sum of the weights. Let's say the weights are all 0, that sucks, right? Sum of the weights, so this is the 0 term, plus the bias. Bias
Okay.
is positive. Crucially, your bias is not very otherwise. So that's how it
you'll probably die.
All right, yeah. If you pull it, should tic-tac-toe should be up.
So this is already up to
Yeah,
date.
yeah.
Try it again. I
Yeah.
literally just pushed it.
It's like, honestly,
Oh, wait.
the most difficult thing to get into one workshop. Like, we're
Yeah.
rushing through it, so there's no way in
Yeah,
hell
that was, I was just wondering.
you can spend an entire course on it, yeah. So, but yeah, I got you.
Oh, wait, in terms of.
I'll post resources.
Okay, yeah. Well, I mean, the first I mentioned it last time. You were here last time, weren't you? So there's neural networks and deep learning.
Yeah,
Yeah, excellent resource. There's a few others like I don't remember the names exactly. I used one in the presentation.
Just William at
Okay.
Cool. And then also, how does your tic-tac-toe file work?
Oh, TikTok.py.
Oh
Okay.
yeah, let me show you.
Wait.
I
Oh,
did that. Okay.
It's empty.
Oh, no, I just
pulled
pushed.
it.
So if you pulled the repository, we put the tic-tac-toe data back up. So what happened? It got deleted.
Did you just download the zip?
Are you sure you
No,
pushed?
I
I
mean
mean,
that
did you just
tic-tac-toe
commit?
Pi, like the generator one.
So wait, what
Oh,
was
it's so.
Are you
I
sure
don't
you pushed?
understand.
Because
Did I? I hope I did. I think it says I did. Let me see. Let me see the graph. So, oh, what? Yeah, what's happening? Data sets.
Okay, so yeah, I didn't really.
Yeah, why is it not updating?
So basically,
Is it on your end or my end? Is it up?
generate a
Status. Oh, okay. Fixed. No, it's my end. Actually, I wonder if I can do this like I can do it really like
so you generate
lamely.
So you can do but it's like on multiple and then basically you enter an I'll explain that. And then so you enter this game, right? Right, and then you say what do you want the output.
Okay, check now. Yeah, pull now. For sure should work.
And then it creates that
Awesome.
in the after that. So why are there 18?
Oh, hey, Will, take that toes up also.
Okay. Whiteboard. We can even try to take that out.
Yeah.
So we're playing a game of tic-tac-toe, put it into the network. So there are 18 inputs, right? So like, let's say like you have a board which is like 9 by 9, right? And you have a game like X, O, X, X, X.
This case, I think.
This guy wins. Sucks, right?
Yeah, go ahead.
You have this state, right? How can we figure out how to put this into a neural network? And neural network takes any real number, right? But like, let's say I said that if a person wins, if a person is O, then their input is 0.5, and if a person is X, then their input is 1, and if it's a blank tile, the input is 0, right? This is it's easy. It makes sense to us, right? But if you were a neural network and you were like trying to discern where these positions were on this board and like what they were, there's a very like fine line between 0.5 and 1. It's almost like you're trying to like tell someone to recognize a picture.
I just put it in
There were slight
I got you.
differences in the shade of gray.
So what did it have to match
Whereas
to?
You have to match it to the input sizes. So if you look at the tic-tac-toe file itself, the there's like something like 5 inputs. So basically, you need to make sure that the inputs are the same as the input layer that you created. So that first element in the network, like, wait, no, it's. So did I say 5? It is not 5. Oh, you're right. Yeah. No, I think it's more. It's for some reason more. Let me do the math.
It's just like so much stuff to go through, but that's essentially what happened. When you do
18. So it's 18 inputs.
that is categorical.
Oh, it's so. Yeah, I think it's the
recognize digits. They don't have.
It's the board for the X player and the O player, and so the zeros that correspond like are the same between each other should mark like an empty piece.
0 and 1, and it's.
And then the output, there should be 2 output nodes
The
too.
network should give you a
Yeah. Sorry about that.
That's
Good to
how
go.
you
Yeah.
update me.
Yeah, no
So,
problem.
in
Thank
this
you
case,
for
right,
like letting us.
Yeah,
We
so
even did another test later.
I guess I'll see you guys
Where you
later.
have 2 outputs.
Yeah.
You say, okay.
Definitely.
What is the probability that